Okay, welcome to the second part of bayesnet. So when we in the first session we talked about a couple of things. I'm just going to recap those for you. We talked about something called dependence, fully dependent, conditionally dependent, conditional independence, and then we talked about full independence. So if there are two variables A and B, they are conditionally independent of each other given C. What I mean by that, if there is A and B and there is C influences each of them like this, then we can say A is conditionally independent of B given C, also written as probability of A given B and C is probability of A given C. Also can be written as probability of A B given C is probability of A given C multiplied by probability of B given C. We also learned something interesting. We learned that how to calculate parameter in a Bayes network. We learned that also. Now, what else did we learn is we learned something that if you have n variables, x1, x2, up to xn, they are determined by a Bayes net. So if I say what is the joint probability of x1 up to xn, so you can say this can be broken down into probability of x1 given the parents of x1 multiplied by p of x2 probability of x2 given parents of x2. So this we can multiply these terms. So rather than saying okay total independence, we have each term depends on its immediate parents. We have written this down also. Now we have also seen one more thing is if I ask you probability of x and y. Now you know that x is true. You don't know anything about y. So what do you do in such a case? Well, what do I do is I sum out y. So I can say probability of x is true. So let's say x equal to 1. 1 means true. So probability of x equal to 1, or I would say probability of x and y equal to 0 plus probability of x given y equal to 1. So I can write it down like this. And maybe y is the parent of x like this. So then I can say the first term can be broken down into, or let's say it is the other way around. It is x giving y. So I can write it down as probability. Okay, you can do it either ways. So this would give you probability of x. X is the top part and probability of y equal to 0 given x. Plus second term would be written as probability of x multiplied by probability of y equal to 1 given x. So this is called summing out over what you do not know. So this is, what we are doing is we are summing out y. Similarly, you could sum out more than one thing. So I know that A is true and I want to find out probability of A, B, C. So you do not know whether B is true or false or C is true or false. So I'm going to write double summation, one summation over B, one summation over C, and I'm going to say probability of A. Generally, this is, summation over all values of B, summation over all values of C. So, this would give you four possible sums. So probability of A with B equal to 0, C equal to 0, plus probability, you know that A is true. Probability of, So this is critical to understand our next thing. So probability of A given B is equal to 0, C equal to 1 plus probability of A given B equal to 1 and C equal to 0 plus probability of A given B equal to 1, C equal to 1. So this is what will be broken down since we have double summation. So there will be four such terms. Then what you are going to do is you're going to say, okay, A I know has already occurred. So B and C. Now you can say, okay, A influences B and A influences C. Now you can proceed and break this term down and you can say I'm going to have four such terms and proceed further. So that is what we learned in the previous or part one of BaseNet. Now let's carry forward, and this is interesting part is what are the type of queries that you can run on a Bayes network. So we know that in general the Bayes network we run a query like this: probability of some q given evidence. So probability of this query, so q is query and e is evidence. So given this evidence, what is the probability of this query? So there are three types of queries that can exist on a BaseNet. The first called diagnostic query. Diagnostic means using the evidence to infer probability of a cause. So suppose cough causes pneumonia. Now what happens is this is known as a diagnostic query. That is what the doctor does. That's called diagnostic. Is somebody is coughing. So what's the probability that they have pneumonia? So probability of pneumonia given cough. So what do you know? You know the effect to evidence of effect to infer probability of a cause. Oh, I'm sorry. I take the whole thing back. I take the whole thing back. I'm sorry. So I take it back. Pneumonia causes cough. Cough doesn't cause pneumonia. Pneumonia causes cough. So this is the scenario. The doctor observes that cough is true. Pneumonia causes cough. So the diagnostic query would say, okay, somebody is coughing. What's the probability of pneumonia given coughing? So use evidence of an effect. So this is effect and this is the cause effect relationship. Pneumonia causes cough. So what is the evidence of effect to infer probability of a cause? This is called diagnostic query. So this is important. I hope you understand this part, which is there is always a cause effect relationship. So cause effect, that is the relationship in a network or a Bayes network. So you use the evidence of effect to infer the probability of cause. That's called diagnostic query. Okay. The second is causal inference. So it's the other way around. Use evidence of a cause to infer probability of an effect. So pneumonia causes cough. So we know that somebody has pneumonia. What is the probability that they will cough? Probability of cough given pneumonia. Or use evidence of a cause. So cause effect. So use evidence of a cause. This is known to us to infer probability of an effect. Okay, that's good. So diagnostic query, causal inference, because the cause we have figured out that it is true. Now using causal inference, you can figure out the probability of a child. The third one is more interesting. It is called explaining away. So let's say this: smoking and pneumonia both causes or both cause cough. So here's the deal. I know that somebody is a smoker. So when I put this means I know smoker, the person is a smoker. I know he's coughing. Now, what does that do to probability of pneumonia? So it is intercausal effect because um, evidence is smoking equal to true. So what is the probability he has pneumonia given certain evidence? Evidence is cough and smoking. That is called intercausal because we want to see how this affects this. In general, it could be, anything that is not parent child. So this is child, this is parent. Parent child, we know there are two cases. Then there is something else, which is D, for example. So now you are wondering if P affects D. So three type of that you can run and diagnostic, causal, intercausal. Okay, let's move along to the next one. And this is our details of each one of them. So let's look at what diagnostic query. This is a little bit detail of the same thing. I have evidence that the person is coughing. So this is cause, this is effect. This is again another cause, cause 2, this is cause 1, and this is effect 1, and this is effect 2. So I know that the person is coughing. Effect is true. What is the probability of pneumonia given cough? How will you figure this out? That's one of the questions. I want to figure out probability of the person having pneumonia given that he is coughing. So how will you figure this out? Because cough depends on two things. Smoking, pneumonia. This is what you want to find out. So given cough equal to 1, what is the probability pneumonia equal to 1? That's what this means. Now, since you are not given anything about P, sorry, you are given what is the probability of pneumonia? So you are given this probability of pneumonia given cause. What about the smoker? Is he a smoker or not? Well, I'm not sure. So to figure this out, you have to say this equal to probability of pneumonia and S given cough summing out S because I do not know anything about S. I think that's the answer. Uh, so that is one way to do it. There is also another way to do it, which we'll see in a minute. Um, so let's not do it this way. This is although one way of doing it. So another way of doing it is using the definition of conditional probability. So conditional probability says probability of pneumonia given cough is probability of pneumonia and cough divided by probability of cough. Okay, so let's look at the numerator. Numerator is probability of pneumonia and cough. So I can say sum out over smoking probability of pneumonia and C. You could put this or you could put a comma. It's one and the same thing. So I could say pneumonia and cough. So I wanted to have a better notation. That's why I did that. So probability of pneumonia, cough, and S, all values of this. That is what I mean by the numerator. So we know we want to find out this Pn equal to 1. C is already equal to 1. So what do I do is probability of pneumonia, cough, smoking is equal to 1 plus probability of pneumonia, cough, smoking is equal to 0. I'm summing out over this thing. Now, what can you make this as? What can you break this down as? I can break it down as probability of smoking equal to 1 multiplied by probability of pneumonia equal to 1 multiplied by probability of cough equal to 1 given S1 and pneumonia when. That is the first term. The second term, obviously, you can break it down in a similar way, and this will be, I leave that up to you to figure that out. So, as I said, first you use the definition of conditional probability, which is the numerator, which is this one, cough given pneumonia and probability of pneumonia. And then cough given pneumonia, you are actually breaking it up into two parts, which is the same thing that I told you, which is this plus this into this. So, and then you can figure this out. Let's see if that is true. So this means the second one will be probability of smoking equal to 0, probability of pneumonia equal to 1, and probability of cough equal to 1 given S equal to 0, pneumonia equal to 1. If you break this whole thing down, and so you would say this is a common term. So Pn equal to 1 is 0.1. You're going to take this as 0.1 because this is a common term. Then probability of S equal to 0. S equal to 1 is 0.2, and this big term is probability. Okay, yeah, I know what it is. Probability of this is, I've taken this out common. Cup 1 given 1 and 1. So parents are true. So parents are in a true and true state. True and true state. The child being true is 0.5 multiplied by 0.95. Plus the other term will be S equal to 0. S equal to 0 will be obviously 0.8. And then we have to say S equal to false, which is no, parent equal to true, that is 0.8 again. So this multiplied by 0.8. That will be the numerator part. So this will be this part, if you follow the whole thing. So that will be whatever has done here, probability of this whole term that we have been doing, divide, which is numerator is 0.83. So this will be 0.083. And then probability of cough. What is the probability of cough? Well, you can figure this out. Probability of cough being true. So divide that by cough and you will get the answer. So how do you figure out probability of cough? Well, you have done that before also. So now you can figure out the probability of cough. Where have we done that before? Well, we have done that before idea. Probability of cough means total probability of cough. And we have done that earlier. If you are still wondering how to do that, well, we sum up both the parents. I think we did that somewhere. It is probability of cough, and so we sum out the whole thing. So we have done this earlier. Now so we have the answer here. So this is the diagnostic query that we talked about here. Diagnostic, again, you are given the evidence of effect, you want to find out probability of cause. Okay, diagnostic query. Causal queries. Causal query is the other way around. I want to figure out the probability of cough given the person has pneumonia. So I already know the person has pneumonia. What is the probability of cough? So again, if you, how are you going to break this down? Well, I'm going to break this down as probability of cough and pneumonia divided by probability of pneumonia. So in the numerator, I don't know anything about smoking. So I'm going to sum up smoking, probability of cough, pneumonia, smoking, sum out of that divided by probability of pneumonia. Then the numerator, let's worry about the numerator, probability of cough, pneumonia, and S equal S, where I'm summing over S, will be two terms, probability of cough, pneumonia, S equal to 0, plus probability of cough, pneumonia, S equal to 1. This will be the numerator, and then you can break it down as just like before. Um, okay, and you can break it down just like before to get the answer for the numerator. For the denominator, you will have to say what is the probability of pneumonia. This will be easy. It is going to be 0.1. If you do this whole math, and you will see that um, so you're summing out over smoking. So probability of summing out the numerator is this much. So probability of cough given pneumonia. Okay. So that's going to give you the same answer, this answer right here. And you're going to get the result. Although they have done it in a different way. What they have done is they have simply said this and they have summed out over smoking, but you will get the same answer. Okay, now that is part two. The third type of query, which is more involved, is I know that somebody is a smoker. What is the probability that he has pneumonia given the person is coughing and smoking? So you are given evidence that this. So how would you figure this out? Probability of somebody has been pneumonia given they are coughing and they are smoker. Well, that's interesting. You have to, think about this, how to do this. You have to think about it, and maybe you will say probability, numerator, definition of conditional probability, CS, um, divided by, hang on, so yeah, divided by probability of CS. That is one way of doing it. Uh, so this way you require summation over CNS. That's one way. Obviously, you could do it another way. Let's see what they have done is uh, they have used the Bayes property. So what they have done is taken this thing right here, and instead of using the definition, we have used the Bayes property. So which means probability of cough and smoking given pneumonia multiplied by probability of pneumonia divided by probability of cough smoking. So what is the probability of cough smoking given somebody has pneumonia? Cough smoking given pneumonia. So how would you figure that out? Well, you can say the person has pneumonia. I know that. Now, what's the probability of cough and smoking? So, which means cough, smoking, given pneumonia equal to true. So, smoking is yes, pneumonia is yes, 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 coughing is 0.95. Okay, so using this definition right here, and okay, they are doing it in a roundabout way. If you look at the answer, they are actually doing it in a very silly type of a way. They are actually using the same definition again. So it is probability of pneumonia, cough, smoking divided by probability of cough and smoking. That is what they have done right here. So this is the numerator, this is the denominator right here. And the way you figure out the numerator is by the technique I just told you. Probability of the numerator can be figured out very easily. So that means it is how do you break this down? You can say probability of Cough equal to 1, probability of smoking equal to 1, then probability of, sorry, this is not cough, this is pneumonia. Probability of pneumonia equal to 1, then probability of cough given 1, 1. This, which means 1 and 1 plus probability of CS. Coughing, smoke, again, the way you figure that out is you sum over pneumonia, and then you will get the answer. So again, you have to do this whole math right here, and you will get the answer, right? So the three type of queries, which is the more important thing to understand, the math will, will figure that out. Math is, there are various ways of breaking it down, but right now you have to understand the three type of queries, and that will be nice. Now, we know that there are three type of queries, which is fine, but how can I see how dependency travels on a network? That is the important thing, is does dependency flow from child to parent, parent to child, side to side, which is what I mean by that is, if that's a more important question. If I know this, does it affect this? If I know this, does it affect this? That is what first I need to do. Does this influence this? Does knowing this, I know the temperature is true, does that somehow affect smoking? So does dependency flow from here to here? Does dependency flow from here to here? I need to know, like, rather than doing all this complicated math, I need to know that, for example, here, this, and this, and this. Does knowing this influence this? So I know the state of this. So does it influence this? So one way of doing it is you could go back here and go back, see if it influences, go back here, go back here. Now, people designed an easier way to do this. They found an easy way. I'm sorry, my mouth somehow got dry here, so I'm trying to drink some water. So now, does dependency flow on a network? That's the basic thing. Dependencies and conditional dependencies on a base network. This is tracking the flow of dependency. Does dependency flow in this direction or that direction? That is what we want to do. Now, before we go ahead, we need to understand the Markov assumption that we made. Markov assumption says a variable x is independent of its non-descendants given its parents. Let's break this down. Let us say S, and I know the parents of S, which is flu and allergy. So flu and allergy, and then it is headache and nose. This. Does S have any non-dependents? Answer is no. S, the parents of S are FA. What are there any non-descendants? No, because these are the parents, these are direct descendants, so there is nothing to worry about. S. H, let's look at H. Does H have any non-dependents? Well, H, the parent of H is S. Parent of H is S, which is fine. Any non-descendants? Well, non-descendant is anything that is below here. Sorry, descendant is anything that is below here. Descendant is which is neither the parent nor anything here. FAN is the answer right here. So what would the Markov property mean? Markov property can mean here H is conditionally independent of all of these F, A, N, given what? Given immediate parents. Immediate parents of H R is S. So given S, this is what it means. Similarly, if you look at N, it is the same thing, but the other way around, it is this thing. Then you have F. So F has nothing above it. And does it have any non-descendants? Well, A is a non-descendant of F. So which means F is this A, but there is nothing on top of it. So I can say F is conditionally independent of A with nothing below it. So it's kind of the same thing as saying independent. Similarly, A is independent of F. So you have to understand the Markov assumption. Now, some people, which is a lot of people, say that X is independent of everything given its parents. That is not true. X is independent of its non-descendants given parent. So, which another way to say that X depends on its children. Okay, now using Markov chain or any other assumption, how can you break down this joint probability? Well, we have seen that many times is you have to first learn which term to factorize out first. F A F A. Sorry, I'm moving here. I'm moving from here to here. F A F A S given F A S here. Then H given S, N given S. So we can figure the joint probability as a product of terms. So this is important because we can figure out probability of x1 like this as probability of joint or the product of certain terms, which is helpful because I don't have to do anything much. I simply have to break it down into parts and compute the parts. So we have seen a lot of things. Now, as I said again and again, is can you figure out a way to say if dependency travels on a network or not? So if I know A, does dependency flow from A to B? Which means if I know A equal to 1, then does the probability of B change? And so on. That is what I'm looking for. So that would be a better than figuring out whether A is true, computing effect on C, C's effect on B, and then figuring it out. It's like the question we had earlier: train strike A and B. So when we said A is true, then we had to go back to the parent and figure out if probability of A is true, what's the probability that C is true given A is true. Then we updated this and then we updated this. So we saw the probability that dependency flows. So that was a very painful thing to do. Now, is there a graphical way to figure all this out? Well, let's look at this connection right here. We will see this multiple times, but let's give you an example. So what is probability of A and B given C? A and B, this given C. What am I trying to prove is I'm trying to check whether A is conditionally independent of B given C. So how would I prove this? I would say if this is equal to probability of A given C multiplied by probability of B given C, if I could prove that, then I would have proved this. Now, this is what I want to start with, and this is what I want to come at. So let's look at left hand side. Probability of A, B, C. That will be probability of A, B, C divided by probability of C. Now, what is probability of A, B, C? Okay, so I know that C is true. That is my evidence. Now, probability of A, B, C. Can this be broken down into something? Well, we know the Markov property and we know other things. So we know that this can be broken down into probability of C, then probability of A given C multiplied by probability of B given C, divided by P of C in the denominator. Now you can say, how did I say numerator is equal to this? We learned it by, how did we break it down like this? We learned by applying first order Markov model. What does the first order Markov model say? It says A is, given this, A is totally dependent on the parent. So probability of A with something else is simply probability of, okay, let's see this. Probability of ABC is probability of A given parents of A multiplied by probability of B given parents of B, and so on. So A is this, parents of A is C. Similarly, the other way around. That's how I broke the numerator into this parts right here. Now, if you notice, this is the thing right here. Denominator is this, numerator is this. It goes out. So I have proven that probability of A, B given C is probability of A given C, B given C. And so I have proved this thing. So I have proved this part. That means that for this type of a connection, given that I know C, so this is an important thing. So given that I know C, that is what we started with, right? Can you show that A and B are conditionally independent given C? So given this person, given evidence, then these two do not depend on each other. So given the C, interesting question to note. And if you did not understand it, please stop and go through this again. So I look at this left hand side. I broke it down into this by using the definition of conditional probability. Then the left hand, this numerator, that is the thing that we can break it down according to this Bayes rule, not Bayes rule, sorry, the graphical property and Markov rule. I broke the numerator down like this, and then I saw that there is a C in the numerator, C in the denominator. I got rid of it, and then I proved the thing that I was supposed to prove. So this will also be known as a, later on we'll talk about this as a diverging connection. Why? Because you see one and it has two things going out of it, diverging out. So we'll talk more about such cases. In fact, we will see that there are a couple of scenarios that play many times. Now, A is conditionally independent of B given C. Now, can you say that there is a general independence? No, there is no general independence. If I could prove that probability of AB is equal to probability A multiplied by probability of B, if I could prove this, then I would prove that A, B are totally independent. But you will see that you cannot prove this. Why? Because they even give you that answer. So if you want to do this, you would say sum out C, probability of A, B, C. That would mean probability of, if you're summing out C, that would mean probability of C, then probability of A given C multiplied by probability of B given C. Probability of C, A given C, B given C. Can you break it down into anything? No. So in general, no. Only when this guy is present, they are independent of each other. So the flow of dependency tracking means, does this influence this? Does this influence this? And so on. So it's called dependency tracking, like we have talked about many times, is tracking the flow of dependency on a network. So given this, are these two depending on each other or affecting each other or not? This whole concept of tracking dependency is called deseparation, which is knowing if two nodes are dependency separated or dependency separated if there are two nodes like this, and there are a whole bunch of scenarios like this and this and this. I want to check if these two are dependency separated or not. Dependency separated would mean that given this guy or this guy, A and B. So let us say given this person C. So I want to see whether A and B are dependency separated given C. So if I wanted to show this, I could show that probability of A B given C is equal to, like always, probability of AC, probability of BC. If I can somehow prove this, then I would have proved that A and B are D-separated. If I cannot prove this, then they are not D-separated. I hope this is clear to you. For example, you could have, various situations. I have this sort of a belief net, base net or belief net, and now there is one thing as thing when we will analyze the flow of dependency, we somehow ignore the direction of the arrows. We'll do that going forward. So when we talk about path going forward, so path will be undirected path, which means you do not have arrows. So I can see there is a path from R to A, which is there is a path from R E A. Is there a path from R to C? R E A C. And so another way I can figure that out. So when we talk about path in the next parts, next slide, we will talk about path as undirected path. So keep this into mind. Now there are three cases for dependency separation. So the three cases are as follows. So there are three nodes, x1, x2, x3. There are three such nodes. Suppose I know this. Does that prevent dependency from flowing? That is what we are going to check. Now, suppose the center one, I'm going to call it Z. So, in fact, the path, this is the path from here to here, x1 to x3, this is the path. If the path contains any node such that so a path is blocked if it contains node such that Z, there has to be some node Z that it contains one incoming and one outgoing arrow. So again, this path is x2, which is series of paths. Like x2 could be a long chain of paths. If there is a Z inside x2 path such that it has one arrow coming in, one arrow going out, then the dependency will flow. So this is called serial connection. Another, well, there has to be a more firm way of saying it. If I know Z, so okay, if I know Z, and um, then the left hand side, which is x1, will block x2. Okay, first case. Okay, so there is a path from, suppose there is a path from here to here, and there is a node Z in the path. So this is x1, this is x3. This is the path. Now there is one node such that it contains one arrow going out, one on this side and one on this side. So if there is a Z node and I know evidence about it such that it is like this and I know Z. Okay, the third connection is, so this is known as diverging connection. Now the third connection is converging connection. So you have x1 and you have x3. So you have this thing, you have this thing, and there is a node Z that has two arrows coming in. That is called converging connection. So now we are ready to do something interesting. We know that in a network, in a base net, for um, any intermediate node can be one of three types. It could be serial, which is this. It could be diverging, which is this, or it could be converging, which is this. So that is, inside story. Can you figure out a node, a binary node, which is neither of them? Well, as I said, it has to be an intermediate node, not a final node. So if it was a final node, you could say this is the final node, but I'm not saying that it is a final, it is intermediate node. So that is where this whole thing builds up. And I hope this is clear to you. And if not, please stop, re-listen to it, re-look at the video, come back, and if you have questions, please let me know. So this is a serial connection, and in a serial connection from x1 to x3 via x2, so x2 is an intermediate node, um, evidence is blocked when we have evidence about x2. So if you have x1, x3, and they are a serial connection at x2 like this. If I know this center person, then evidence will be blocked from here to here. If I know the center person. So this is the graph which is intermediate. If you do not know this, no problem. If you know this, blocked. So if knowing the center guy prevents the flow of dependency, how can you prove this? Well, if you were able to prove probability of x1, x3 given x2, if you can break this down into probability of x1 given x2 multiplied by probability of x3 given x2. If you could prove this, well, that would be one way of doing it. There are many other ways of doing the same thing also. You could also say probability of x1 given x2, x3 is equal to probability of x1 given x2, for example, and so on. So can we prove this analytically? Okay, let's try. So let's look at an example of this. This is a converging. So if I know the center guy, does it help me? Now let's say I want to break down this term, the joint probability of this term. According to Markov property, what would this be broken down as? Probability of x, probability of y given x, probability of z given y. Now this is fine. Now suppose I want to say probability of z, which is this last guy, given xy. If I could prove it, if that probability of z is this, then you would be done. Let's look at this left hand side. What can you write the left hand side as? Probability of xyz divided by probability of xy. Numerator we have already broken down earlier. Probability of x, probability of y given x, probability of z given y. And the denominator is x and y, so probability of x and probability of y given x. This. So probability of z given xy is equal to probability of z given y. So I have proved this, and I know it might be a little bit complex, but we are simply using the definition of conditional probability and Bayes rule. That's all we do. So I have shown that the dependency is blocked if I know the center person. Important point. So this is the proof of serial connection. Why? Because y is a serial node. So can you do the same thing with diverging connection? So which means I want to prove that if I know x2, then the dependency will be blocked. So let's look at this guy, and my claim is if I know y, then x and z are not dependent on each other. So that means probability of z given xy, just like before, if could prove this, is equal to probability of z given y. Can you prove this? If you can prove this, you would be done. Let's start with left hand side. So the left hand side is can be broken down into according to definition of conditional probability as x, y, z and probability of x, y. Now looking at the network, the definition of the network, the numerator is probability of y, probability of x given y, probability of z given y. Denominator is probability of y multiplied by probability of x given y. Cancel, cancel. This means probability of z given y. So I have proved this thing right here. So now I can say I know this person, which is a diverging connection, if between x and z. So there is x and z. If you look at the path between them, and there is one node which has a diverging connection, and I know that node, then x and z will be independent of each other, conditionally independent. So it's like, for you to do that, you have to say x and z, and you have to trace a path from here to here. And then within that path, you have to discover a node such that there are two arrows come out of it. And if you know that node, then x and z will become, what did I say? It's not y, z. This is x and this is z. So if you have any node y with two arrows coming out and you know y, then you are done. So diverging serial we have studied, which is fine. Diverging we have studied, fine. Now what happens in a converging case? Now there are nodes x1, x3. They are sent, and this is an arrow right here. They are sending path like this, and there is a node between them where two arrows are coming in. So you will see that if in a converging connection, x2 has parent x1, x3. So x2 has parents x1, x3. Any evidence on this center person results in evidence being transmitted. So this is opposite of what you would expect of the other two. So x1, x3. Look at the path between them. In the path, you have a node such that it has two arrows coming in. And then such a node, which might be called Z, if you know it, if you know this dependency will flow, otherwise it will not flow. You can also prove that you can prove that if Z or any descendants of Z, for example, C, if you know C, well, if you know C, then you know the parent, probably. And then if you know this, then dependency will flow. So this is what we mean here. So there is E and B. The path contains a node A which is converging and I know information about A. So it will not block. Even if you have information about C, this will not block. Otherwise it will block. So several things we have studied, and in this case you will see we cannot do anything. I wanted to prove whether probability of x1, x3 given x2, can I break it down into probability of x1 given x2, probability of x3 given x2? Can I break this down? The answer is no. That is why you have this rule right here, that converging is a different scenario than the rest. Okay, so we have done enough of theoretical part. Let's do some practical parts. So let's look at certain examples. And in the example, we will say suppose RB. So you trace a path between R to B. That's the first thing that you do. And I'm simply asking whether D separation R and B, they are D-separated given what? Given I'm not given anything. So no evidence is given to me. Now let's trace a path between R to B. This is R, this is B. So this is the path that I have traced. Path is always undirected. So let's see E. In this path, which is, you have to look at the path, not any other path, but in this path, what is E? I claim that E is a diverging node because two arrows going out. A is what type of node? It is converging node, right? Because I have R, E, A, B. So we have traced the path like this, right? So in that path, I just trace the path first. And then in the path, look at each node and see what type of structure is it. So it's got two arrows going out. So E is diverging. And then look at this path. I'm just focusing on this path. What is A? Well, A has one arrow coming in here, one arrow coming in here. So that is a converging. So first you figure out path and then examine each node in the path. Diverging, if I knew something about diverging, it would block. But I do not know anything about a diverging node. So it will allow this information to, this will not block. And A is a converging node. If I knew A, then it would allow. I do not know A, so dependency will be blocked here. Now you have to say, why it is blocked before, because it is a converging. If I knew this or if I knew this, it would allow it to flow. So this will cause dependency to be blocked. That is the whole thing. We traced a path, and then in the path we had so x1 is R, x3 is B, and the path has earthquake in it. Earthquake is diverging, so not blocking. Alarm, which is converging, and no evidence available about about A. No evidence about A is available, so it will block. So dependency will flow here and will be blocked here. That's the first thing that we consider. So what can you say about separation R and B? So is it yes or no? Are this D separated? The answer is yes, because A does not allow dependency to flow around it. So A will block the dependency, which means they are D separated. Okay, let's look at the same question. In this case, you know A. Well, obviously, if you know converging node, it will allow dependency to flow, and this will allow, and this will allow. So now, whether R and B are D-separated, I want to ask you this question. Answer is no, because dependency is flowing. R, E, A, B. This allows dependency to flow, no problem. This allows dependency to flow. The dependency can reach from here to here. It's like you're tracing the flow of water, and water can flow from here to there. So I know you'll take some time getting used to it, but other than that, it's going to be fun. Now, dependency separated of R and B given A. So in that, we have done this one, example 2. Example 3, R, B given E and A. You are given both nodes. So similar path R, B, sorry, R, E, A, B. I know this, I know this. Now, what type of node is E? Diverging node. I know information about diverging node. So what does that mean? If you can look up the previous thing, it will tell you that this will not allow dependency to flow because you know the center person, and the center person will block dependency from flowing from here to here. And once there is a blocking node, the entire path is blocked. So D separated this and this. The answer is yes, they are D separated because dependency cannot flow from uh, R to B because of the node E. So we have blocking node E. So since E is blocking, there is no question of checking anything else. Now, another interesting question is radio and gas. Radio and gas evidence about moves. I know that the car is moving. Does radio influence gas? So if you want to look at common sense reasoning, you will say my car is moving. I know that. And then I also know whether the radio is working. So I know that the radio is working, moving. Now, does that influence the gas of the car? Can you say both of these things, whether they are true, then can they influence gas? Well, if the car is moving, the radio is working, that means the gas should be there. Similarly, you can say um, given moves, I know that the radio is not working. So gas, um, is there dependency between radio and gas? Given that the car is not moving. So you can see that's common sense reasoning whether R influences G. Radio working influences the gas. So given that the car is moving. So given that the car is not moving. So moving is false. Then I know the radio is working. Does that influence gas? Well, if your radio is working, then the battery would be there. Now, the car is not moving, but the radio is working. What does that tell you about gas? There is no gas in the car. So, according to common sense reasoning, radio should influence gas, given that the car is moving. That is just common sense reasoning. Let us see if that is true. Let's trace a path from R to G. So let's trace this here. Now, I have no knowledge about battery. And what type of node is battery? Well, it has two arrows going out, diverging node. Do I have any information? No. Okay, allows the flow. Ignition converging. Do I have any information? No. Fine. Moves, I know that the car is moving. I know this to be true. That influences S. So I know S indirectly. Now S has two nodes coming in and I know about it. Converging nodes, I know about it. So it will allow. So D separated R and G given M is they are not D separated is false because R influences G given M. Similarly, you can have a couple of more examples. Does are C and F, these two, D separated given that you have information about this node? So now the thing is you can have multiple paths. So you have this path and you have this path. So let's look at the top path. So in the top path, sorry, where is that? C, yeah, C to F. Now if you start from C and look at this path, then what type of node is B? It is a serial node. It's called serial node. What type of node is A? Diverging node. So any knowledge about this would block. Knowledge about this would block. What is this node? It is serial node. So serial node, and you know it would block. So there is question of dependency from C reaching F from the top path. How about the bottom path like this? So what kind of node is B? Diverging. Do I know anything about B? No. Okay. It allows the flow of dependency. How about E? E is a converging node. Do I know anything about E? No. So the dependency is blocked here. So block, block. So they are D-separated. Red path is blocked by D, blue path is blocked by E. So both paths are blocked and dependency cannot flow. Similarly, there is one more question. There are a couple of more questions. So if I can ask you whether B and C are conditionally independent given A. Now here is where it gets interesting. You see the top path. So there is this path at the top. In the top path, A is a diverging node. I know A, so this is a blocking path. Now, how about this path? How about this path right here? B to C. G is a converging node. Do I know anything about G? No. So, if I don't know, this is a block and block. So, B and C answer would be yes, according to me. Block, block. So, they are conditionally independent. Similarly, they have posted a bunch of other questions which you can practice. Um, and I would advise you to practice all these really well. They are very simple to understand and get the hang of it. So as I said again, look at the type of nodes: converging, diverging, serial, and then look at if the information is available or not about that node. So we have finished the BaseNet chapter, and BaseNet, also known as DeepNet, is a very interesting part, and there are a lot of things going on in this thing. You can do a search and you'll see a lot of people doing the BaseNet analysis or research. So after doing that, let me stop this and I'll see you in the next session.